Tactile switches provide a more straightforward hands-on method of human-machine interaction than traditional control systems, which can rely on intricate interfaces. To develop a user-friendly robotic arm controller, this project integrates tactile switches with the PIC16F18875 microcontroller, which was selected for its reliable PWM modulation, analog-to-digital conversion, and real-time control features. The project utilizes the concept of pulse width modulation, which we will be using to modify joint angles, which is the system you will be using 8 tactile switches, which is 2 for each degree of freedom.
So for the source code and simulation, first we have to set the parameters for the peripherals. So first we're going to add a timer. So here we add the timer 2. In here we set the clock source to FOSC /4, then the prescaler to 1:32 ratio, then the timer period to 20 milliseconds. So why 20 milliseconds? So it's because we're going to use the SD90 servo motor, and based on the datasheet, it operates on 50 hertz or 20 milliseconds, meaning that it is controlled by PWM signal, and it checks the width of the PWM signal every 20 milliseconds. So that's why we use that. So next is the PWM peripheral. So in here we're just going to select the timer 2. Then the duty cycle we're going to set to 10%. So why 10%? It's because we're only going to use 10% of the 20 milliseconds that we have set. So it says here from the datasheet that its maximum is going to be 2 milliseconds, which is 10% of the whole 20 milliseconds PWM period. So here we have the source code. So first we're going to initialize the device using system initialize. Then next is we're going to set variables for tracking the current duty cycle. So we're going to we're going to add a variable for initial duty cycle. This is set usually in the midpoint between the minimum and the maximum. So we set here 30 for each duty cycle for each PWM signal that we're going to use. So next is we're going to initialize each PWM module that we have set earlier. Then the next is the main code, the main loop. So this is basically just saying that if switch 1 is pressed, then from the variable duty cycle that we have set initial with the value of 30, it's just going to add increments of 1. Then if else it's not pressed, it's just going to stay at that value, whichever value button is not pressed. So let's say we're going to push the button and set the value until 40. So from 30 to 40, then we let go of the button. The value of that duty cycle will stay at 40. So the next is going to be the same, but it will decrease the value of that duty cycle. So if switch 2 is pressed, it's going to decrease increments of 1 instead of adding. Then if it's not pressed, it will just stay at that same value. So that is basically everything that we put in this code. So we're just going to copy paste the code for the other three PWM signals, and by using the other six switches to control uh, the increments. So next here is we have schematic. Uh, so we have here our PIC microcontroller, our 4 servo motors, then our 8 switches. So first is we're going to connect the data pins of the servo motors to our microcontroller. So we're going to be the ones to set which pins are going to be the PWM output. So in this case, we have set 6, 15, 16, and pin 23 as the PWM outputs. Then is we're going to connect the switches to ground, then the other pin to the input pins. So we're also going to be the one to set this, which pins in the PIC microcontroller are going to be the input pins. So here we have set it to pin 17, 18, then 33 to 38. So next is we're going to connect the power. So we have here our 5-volt power supply, then connected to the VDD of the microcontroller, which is pin 11. Then we have to connect it also to the 5 volts of the each servo motors. Then connect the ground pins to ground, and also our VSS pin of the microcontroller. So that's everything.
When we first implemented the code, it was initially hard to control the servo motor. The servo motor had a lot of debouncing problems, and whenever we tried to control it using one of the two buttons per allotted per motor, per servo motor, it didn't run well. So what we did is refine the code until we got the right amount of movement for each servo motor. And as stated in the last slide, we also used the SG90's datasheet to our advantage and used its parameters directly in the MPLAB IDE and IPE to efficiently make each servo motor work by using the PIC16F as a controller. When we first implemented the code, it was initially hard to control the servo motor. The servo motor had a lot of debouncing problems, and whenever we tried to control it using one of the two buttons per allotted per motor, per servo motor, it didn't run well. So what we did is refine the code until we got the right amount of movement for each servo motor. And as stated in the last slide, we also used the SG90's datasheet to our advantage and used its
Okay, test number
this
2.
project effectively used tactile switches and the PIC16F18875 microcontroller to create and implement a 4 degrees of freedom robotic arm controller. With tactile switches mapped to each degree of freedom, the technology enables simple manual control of the arm's movements. The code was created and tested using the MP Lab IDE and IPE, and the PIC16F18875's PWM modules were successfully used to drive the servo motors. This project effectively used tactile switches and the PIC16F18875 microcontroller to create and implement a 4 degrees of freedom robotic arm controller. With tactile switches mapped to each
Test
degree of freedom, the technology enables. By developing a working robotic arm controller with tactile switch inputs, the project met its goals. PWM motor control enabled accurate motions, while the tactile switches offered an intuitive user interface. This project shows how to successfully combine software and hardware elements to produce a useful robotic system. We recommend improving the code with a strong switch debouncing technique and investigating control algorithms like PID to maximize the arm's responsiveness and using sensor based feedback control for closed loop precision and stability.